Hi, good morning, Joy. So today we will discuss about dynamic programming. Okay, so the slide is already in Lentera, so you can download from Lentera. So this is what we will discuss. So what is dynamic programming? What is a principle of optimality? And then I will discuss a little bit more about recursion itself, and then curse of dimensionality. And then we have at least two examples. One is using network, okay, to solve dynamic using dynamic programming, and the other one is using knapsack. Okay, so what is DP? Okay, so DP was proposed by Bellman, okay, in 1950s, yeah, 1940. So DP is a mathematical method to improve the computational efficiency, okay, by decomposing the problem into smaller and simpler sub-problems. So that is the basic idea of dynamic programming. Okay, so the purpose is to search for the optimal policy for sequential interrelated decision. Okay, so that is the basic purpose of dynamic programming. So you can imagine, you can abstract things into sequential interrelated decision. Okay, so how to use? Okay, of course, because that's the way to do. So you need to transform your problem at hand, okay, so into sequential decision process. Okay, so how you will get optimization? You find the optimal policy involving say n components, okay, and then those n components you will separate into n stages, and then this sequential decision process you will put in recursive fashion. Okay, so I know a lot of jargon here, so but you will start to learn about it. Okay, the other name of dynamic programming, sometimes we call it multi-stage programming. Okay, and the basis is what is called principle of optimality. So there are many terminologies that you need to understand first before you could understand dynamic programming, right? Uh, Basically, what you have, you can think your problem as a network. Okay? Network is basically directed graph, so consists of node and links. Okay, so the nodes is called state in here. So this is where the decision must be made. And then the decision itself is represented by outlink, okay, from a node. So a link going out of a node is called outlink. Okay, and then what is called decision policy is basically a path from the initial node to the goal node. So then you will have a sequence of links or sequence of nodes as decision policy. Okay, so uh, did you learn about graph theory before in other classes, Joy? So if you are not sure,
Yeah, we did in operation.
reset one also you get, right? So if you're not sure about what is graph, you can visit my tutorial about graph theory. Okay. So what is principle of optimality? Okay, so Bellman in 1957 said that optimal policy has property that whatever the initial state and the initial decision are, okay, the remaining decision must constitute on optimal policy with respect to the state resulting from the first decision. That is the quote. Okay. So that means if we know, okay, how to proceed from an intermediate state to the final state, then we should follow this action regardless how to get to the intermediate state from the initial state. So suppose you have suppose this is your initial state and this is your goal state. Okay, so this is goal and this is your init, right? And then this is your intermediate state. So intermediate. Okay. So now principle of optimality state that if you know, okay, if you know that this line, okay, this line from the intermediate state to the goal state is already optimal, right? If you know how to proceed from the intermediate state to the final state, so you from intermediate to the, this is already optimal, then you should follow this action regardless how you will get from the initial state to the intermediate state. That means, look, if I already know that from intermediate to the goal node is already optimal, okay, so I don't really care about it anymore. All I need to know is I will find again from initial state to the intermediate state, right? But if you think that way, if that is correct, right, and Bellman is basically proving this principle of optimality in his book, okay, that it is correct. So if this is correct, then the way of thinking is now we can use this recursively, right? For example, from the goal node, we know that this is already, the intermediate is the same as the goal node. That means the goal node itself is already optimal. And then the one before the goal node, you check this is optimal or not. If this is optimal, then this is optimal already. And then you go back to the next node before that and so on. Until finally you will go to the initial state. That's how you do dynamic programming. Okay, so here, if we know, okay, if we know the best path from the intermediate state here, okay, to the desired state, the goal state here, okay, for example, this is the best path is already known, okay, then regardless how we get from the initial state here to the intermediate state, okay, we should think of it as recursive. Yeah? So if you know from this goal state, for example, and then you want to go from this goal state, what is one before the goal state? So you will say, okay, this is the one, this is the one, right? This is the one, this is the one. One before the goal state. Then you check which one is the most optimal before the goal state. Okay, oh, this is the one, right? Okay, so L to N is the optimal, for example. And then again, you don't need to care about the one that is not optimal here. Okay, only care about the one that is optimal. So basically, you already remove all the other possibilities by checking just one node before the goal state. Okay. Then say you are already here, right, in node L. Then you said, okay, what is the node before L? Okay, so node before L is, for example, this one, and this one, and this one, right? So let me call different color here so that you will see. I will put it as right. Okay, here, 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 and here, right? So then, what is the most optimal among this red to N to L? So this is probably the optimal one. Okay. Then you disregard everything else. Okay. This is, you don't regard anymore. Okay. Again, so now you are in this state. You go back. What is the node before that? So for example, that this is the one. This is the one. Right? Okay, let's call it blue here. Yeah. So then you will check which one is the most optimal and so on. So basically, principle optimality is you start from the goal state, and then you go back up to the initial state. If you know the best path from the intermediate state to the goal state is already optimal, then regardless how you will get from the initial state to this intermediate state, you should proceed along this best path. Okay, is it clear or not?
Yes, sir, it's clear.
Clear, yeah? Okay, so by doing so, okay, we can breaking up very complex problem into simpler sub problems. Okay, so basically the idea of dynamic programming is to find the optimal substructure. Okay? So the solution to the entire problem will rely on the solution of the sub problems. So this is divide and conquer, right? So dynamic program itself is based on recursion. So what is recursion function? Okay, so recursion function or nested function is a function that calls itself, right? So in this case, you need to have a boundary condition and way to exit the function in the computer code. So in mathematical recursion is sometimes called difference equation or dynamical systems. Okay, so you can check my website. I think you take this morning is what class? Difference equation, differential equation.
Yeah, differential equation.
Okay, so that is the one. That is actually a recursive equation. Okay, and probably after the midterm, I will give you the difference equation there. Okay, so this is an example of recursive function. Okay. So factorial, for example, you see you start with boundary value f1 is equal to 1, right? And then this formula here, you will see this is a recursive formula. Why? Because this formula is called itself, yeah? f n depending on f previous. Fn is f current, and then fn minus 1 is f previous. Okay? Multiplied by the time itself with this n in this case. So of course, if you know the boundary, the value is f1 is 1, then you can calculate f2, right? What is f2? F2 is 2, okay, multiplied by f1. Okay? F3 is 3 multiplied by f2, and so on. So you will get this sequence 1, 2, 6, 24, and so on. So this is an example of recursive function. Okay, so you want to practice this or anyway, this is so easy. Maybe you don't need to practice. Yeah? So basically, if you calculate the factorial recursively, so you will put in Excel. Okay, so 1 before, right? So you will see here that this is just n. In the beginning, you will just say as the same as this one, and then in the second line, you will see that this is f2, right, equal to f1 multiplied by n. So this is the n. Okay. This is another example of Fibonacci. Oh, okay. This is the one that you need to practice in Excel. Can you do this? So you have two boundary value in this case. Okay, f0 is 0, f1 is 1, and then you're supposed to get this sequence. Can you practice the Fibonacci in Excel and then tell me what is your experience?
Yeah.
So So the Excel, no problem.
Yeah.
One,
Okay,
one,
so-
two, three, four, five, correct, right? Okay.
Yeah.
So can you continue this until say 75? So where can you put n also?
Where?
In column A, for example, n. So that is 0, right? Yeah, yeah, n.
Mhm.
Yes, 0.
Zero.
And then that is 1 plus earlier equal 1 plus earlier.
Oh, yeah. Oh.
Same, yeah.
Like this?
Yes, and then continue. Say until 80.
Until 80.
Until 100 is fine. Yeah. Okay, good. Now continue with the Fibonacci. So, what do you think? This is all correct or not?
Hmm.
Hmm. Okay. Before later we will check the correctness. Huh? Later we will
Mhm.
correctness of it. Okay. So at this point, let's try to make the Python one.
Okay.
Okay. So for the Python one, you can just create exactly the same like that. Oh, you make it. Okay. Okay. Print is you need to use parentheses.
Oh.
Yeah. The Python 3 need to use parentheses. Python 2 no need parentheses. Okay, you can print. Does it work? Oh, no, no, no. I know what's the problem here. The 14, 15, 16, you need to put in the beginning.
Mm.
On top. In
Oh.
you probably use
Oh.
shift tab. Shift and tab together. One more.
Okay. Okay.
Then you can run. Yeah.
Mm.
Okay. Joy. Oh, you can the 15 you change into n. Capital N.
Into N.
Yeah. For example, capital N. Okay. And then n earlier in line 13 you put n equal 15.
N equals 50.
Yeah. Okay. And then you can run again. The same. Yeah, you get the same thing, right? Good.
Yes.
So now you can change that n into 150. You can get again. So, oh, you get. Okay, now you can check this with Excel. Especially, okay, your Python is hung, right? 150 is too big for Python.
Oh. Yeah.
So
Yeah, I think it's still right
you see it.
here. We got.
I think after 78 or at 78 it will be incorrect in Excel.
Oh.
So
Oh,
you
it's still loading.
check print I comma f so that you will know the n. Okay, you stop it console.
Control. Restart. That's correct.
Because your Restart. Kernel, eh? Yes. And then N150 is too big. After you click yes, restart kernel, you change to 80. N is up to 80 only. Okay, and then print is I, comma F. Okay. Okay, so that you will see the actual value, right? Good. Run this. Oh, getting slower and slower.
Yeah.
Because this procedure is recursion. Super slow. And not only slow, probably you cannot solve it because your memory is not enough. Okay, up to 37 only. So I think up to 37 still correct.
Yeah, still correct.
Okay. At 78 probably is incorrect. Wow, become too slow, right? So
Yeah.
solve that. How do you solve that? This is not too slow. You see recursive problem. Okay, this is getting much and much bigger. So solve it in Excel. You can solve it, but this is incorrect. Okay, in Python, when you do it, uh, you see you cannot even solve 39 or 40. So okay, I will show you how to test this is incorrect. Okay, in Excel,
Okay.
you can go to my website. I will put in chat. To this website about digital root. Okay, and I think I have a version to prove to you. About the okay, maybe this one in chat. Where is the chat? Okay, please. Can you check the last there? This is about Fibonacci sequence, right? F1 is 1, F2 is 2, okay, and you continue down a little bit, you will see down. So in 72 is like that, 73, 74, oh, 74 is a problem. You can start to see in Excel like this, okay? And if you want to test, you test the digital root, okay? You test
Okay.
the digital root of Fibonacci. Okay. There is a pattern in Fibonacci number that have every 24 digit, it will create a pattern.
Okay.
So how do you compute the digital root is that formula down there. So you can create in column C in Excel. So you can go to column C in Excel and put that as digital root, DR or digital root, digit root. Okay. Okay, so the formula is, what is the formula? The formula is the next page, right?
Oh, this one.
Yeah. So that 1 plus mod 9 x minus 1 comma 9. In Excel, that would be 1 equal, yeah, equal 1, and then mod, the x is the Fibonacci number minus 1 comma 9.
This one.
Minus, yes, minus 1
Minus 1.9.
comma 9.
Like,
Close it. Oh, what
oh,
is the comma, not point. The divisor is not 1.9, 1 comma 9.
Oh,
Okay.
okay.
Okay, then you can continue. Okay, you will, after 14, you will see, continue. So after 24, continue until down, until the end. Okay, there is a pattern in Fibonacci, digital root of Fibonacci number that every 24, it will repeat again.
Oh.
Oh, what happened?
I also have the same problem. I have
You
like
have
the
same
error
problem.
on 66.
Oh no. Wait. Okay. So modulus, okay, modulus have a problem. In that case, you can use a floor function. Okay, if you have a mod have a limitation up to 9-digit number, right? Okay, so mod in Excel have problem. So in that case, you can use the next digital root is x minus 9 multiplied by floor of x minus 1 divided by 9. That's another formula to compute digital root.
So the
Can you see it?
so the number minus
It
1
1
times
no x
means
minus x minus 9. Okay,
x
I will scan my screen so that you will see.
9.
This is the one. Earlier this one, right?
Ah, okay.
Okay. You go down a little bit.
Yeah.
Okay. So
Oh, yeah, I found it.
not have limitation up to 9-digit number. So your number is larger than 9 digits, so Excel cannot take it. So then you can use this. Okay, x minus 9, x minus 1 divided by 9.
Minus 1 divided
Yeah, this is floor. Yeah, this symbol is floor function. This Robert Sawyer is an engineer from NASA. So he contacted me after I posted this digital root tutorial, and he tried to improve my tutorial. So
It will always result in 1.
really?
Wait, did I input the wrong form? X minus 9 multiplied by x minus 1 divided by 9, right?
X minus 1 divided by 9,
Oh, yeah. X minus 1 divided by 9.
and then you take the floor function. Floor function in Excel have a digit significance, so you put 1. Can you share your screen?
Okay.
Oh,
I can help you. Oh, very small. Wait.
This one, right?
X. Okay, X is the Fibonacci, right?
Yeah.
Okay, and then X is the Fibonacci minus 9 multiply by floor. Yes, that floor. Okay, close.
Oh. At first I had like negative values, then I changed it, then I have one. Okay, now it works.
Okay, good. So now you check. Okay. Wow. Okay. So you can check. Can you check the pattern? I think that's enough.
Okay.
Okay. So can you check the pattern there? What happened? The digit root is also negative.
Yeah.
That's nice. So start from one. Start from one. Okay. 1, 1, 2, 3, 5, 8, 4, up to 24 and up to 23 and 24, right? And then is it come back again?
Yeah, it repeats itself.
It repeat, right? So until 25, yeah, in your case, yeah. And then
Yeah. 25, we have a new one at 26.
at 25 is the same as 0.
Yes.
So you can color that so that you will know this is the whole pattern. Okay. And again, in that case, 48, right? Or 49 in your case.
50. Yeah,
Yes.
yeah, 49.
Yeah. Okay. Repeat again, right? Okay. And for 24 times 3, how much?
24 times 3, 72.
Yeah. Supposed to be repeating there. Is it 9? Or
Yeah.
that 73, that one is the same 9, right?
Mm.
Uh-huh. Then you check the pattern. So something is wrong, right?
Yeah.
Uh, it's supposed to be 1, 1, 2, 3, and then supposed to be 5, but it does not.
Yeah.
Right. So that means Excel cannot compute Fibonacci correctly at that
Mm.
big number.
Why?
Why? Do you know why?
Like, is the number too? I don't think the number is like that complicated. It's just really big.
Yes, it's really big. So computer, the way to compute is using especially floating number, right? In Excel, they use floating number. Floating number is basically a string with two string. One is in front of the decimal and then behind the decimal. Okay, and then they have some limitation of that. So when the number is so big, they will truncate. It will truncate the number. So that's why it will produce some number, but you see it's so big, just plus 15, right? E plus 15, but that number is incorrect and it's not precise. Okay, so digital root is like the root of the number that actually can show you the pattern, right? So you can see here this is not correct anymore. So in Python, okay, the number in Python is already big num. So that means already big number. So you can calculate that correctly in Python. Okay, but the problem is very big and very slow. Okay, you try that slowness in Python. Oh, Livy, did you manage to finish? Oh, you finish it, right?
Wait,
Okay.
I have a different one with Leafy.
You use a better version, right? So this is an iteration rather than recursion.
Yeah.
Yeah. So correct. If you use a recursion, okay, the way to compute is very slow and incorrect. So from this Python, you can create a new function, dr, for example, the digital root, and then you can check, okay, and the will be correct. Right. So let me show you here. Okay, so I create the Fibonacci earlier, right? And then now I created the digital root, dr, using the earlier formula, or you can use the floor function. It's the same thing. Okay, and then you can print the dr with the Fibonacci. Now, yeah, you can get that. So this is another example of recursive function. Okay, this is called affine function, where the yk plus 1 equal to a times yk plus b. So it's up to you to insert the value of a and b. Okay, then you will have a boundary condition of y0. So using this affine function, you can actually compute, for example, y1 is a times y0 plus b, y2 is equal to a times y1 plus b, right? So then we can put all into y0. Okay, so the y1 earlier is y0, a y0 plus b. So you can put it all into y0. The same thing, y3 is a times y2 plus b. So again, you can put that into y0 because you already have in earlier, and so on, right? And finally, you can see, okay, if we simplify, the last part here is actually a geometric series. Okay, so we know in from mathematics, okay, geometric series have this formula. Okay, so there's a closed form from this geometric series. A 1 plus a square up to a n minus 1, okay, is equal to n if a is 1, equal to 1 minus a exponent n divided by 1 minus a if a is not equal to 1, right? So in that case, we can solve this affine equation earlier, okay, to become like this. Okay, so up to here, is there any question? Livy, Joy? No, no problem, yeah.
No, no problem, sir.
Okay, so next. If you have a data, right? So in the data table, okay, each row is called record. Each column usually it's called variable or field or feature. So sometimes we call it dimension. Okay, so there is terminology is called curse of dimensionality. What does it mean? It means when your data has a lot of variables, so that means a lot of dimension. Okay? Now each variable have its own set of value, right? For example, gender have two value, male and female. Okay? Color, for example, you decide to have 24 color, say eye color, for example. And then if you can see you have only two variables, gender and color, how many combination? 2 times 24, right? So that is already 48. Now, if you have three variable, for example, what variable in the third variable? So say the third variable is the Likert scale of 1 to 5 or -2 to +2, okay? 5 values. So again, 48 multiplied by 5 values. So when you have a lot of variables, each variable have its own set of values. Okay? The number of combination to be searched become exponential. So this is called combinatorial explosion. Okay, so even if you have only two values, binary variable of n dimension, okay, the number of possible combination become 2 exponent to the n. Okay. So earlier in our Fibonacci recursion, okay, if you look at the call tree of Fibonacci 5, for example, Fibonacci 5 will call Fibonacci 4 and Fibonacci 3, right? And then what happened is Fibonacci 4 will call Fibonacci 3 and 2. Fibonacci 3 will call Fibonacci 2 and 1. Again, Fibonacci 3 will call Fibonacci 2 and 1. Fibonacci 2 will call Fibonacci 1 and 0, and so on, up to finally we'll call Fibonacci 1 and 0 at the bottom, right? So you will see this is the sub-problem that are computed. And sub-problem in here are recalculated again and again, right? So you will see that, for example, Fib2 is called 3 times here. And how about Fib1? Fib1 is called so many times, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 times of Fib1, yeah? And so on. So this is lead to exponential time algorithm. That's why your computation earlier becoming very slow. Yeah. So dynamic programming solution, okay, is to use what Joy has shown earlier. Okay, this is very fast. Okay, so using this computation while loop or using for loop in here. Okay, this is constant O1 space and linear time. Okay, just repeat it n times here. The loop represent the n. So this is the loop that you call n time, right? Okay. So that's why this is called linear on time. So the loop repeat n minus 1. Okay, and this is fast. The result is the same, and the space is only 1. So you can try this, Livy, if you did not make it yet. Okay, so this is a dynamic programming solution. Okay, now the general step in dynamic programming is first you need to define the optimal value function. So you need to define the function, okay, and then you create the recurrent relation, and please note the boundary condition. Okay, let's take an example of a network. Okay, so this is supposed to have a network from A to B. You want to find the shortest path. Okay. The numbers here, for example, A to C is 1. That is the cost. Okay. So can you find the shortest path from A to B? This is A. This is B. Okay. So the way to do in dynamic programming is to think in terms of stages. Okay? So that's why we call it multi-stages. So a stage is a portion of problem, sub-problem, that contain a set of mutually exclusive alternatives from which the best alternative is to be selected. So in our problem, how many states? Okay, how many states do we have in our problem? What do you think? So we can set here. So from B, okay, earlier state is O and P. So this is the state N, right? So this is N minus 1, okay, N minus 2, and so on. So this is stage 1. 1, 2, 3, 4, 5, 6. So you have six states in here. Okay, so each line here represents the states. So first we will define what is called optimal value function. Okay, so let's call this SK. So what is SK? SK is the minimum cost, okay, from node K to the goal node, which is node B. Okay, node B is the goal node. So the minimum cost from any intermediate node K to node B. Okay, that's how you define the optimal value function, from any intermediate node to the goal node. Okay, so that is the function. So for example, SC, okay, that is the minimum cost from node C to node B. SD is from node D to node B. Okay, so now in node A, from node A to node B, how are you going to do? There are two possibilities, right, from node A. From node A, you can go to C or D, correct? This is A, okay, this is C, this is D, okay? So from node A, you can go either to C or D, okay? So we don't know from C to B, okay? We don't know from D to B, right? We don't know. But we can just say, I will repeat again. We don't know from C to B. We don't know from D to B. Okay, can you see in this drawing? Now, but we know there is a minimum cost from C to B. What is that? We call that SC, right? We already know, we already give name. Okay? SC is the minimum cost from C to B. And SD is the minimum cost from D to B. Okay, so this is C, this is D. So in that case, now we will say, okay, if I want to get SA, that is what? Minimum cost from A to B. B is the goal node. Okay? So that means all I need to do is to find the minimum 1 plus SC or okay, 0 plus SD. Correct or not? Can you create this formula or not? My question to you. Joy, Livy.
Yeah, I understand.
You understand? Livy, do you get it or not? If not, we cannot continue. We need to understand this first. You give questions so that I will know what you don't understand. This is the most important part here. Okay, this is based on principle of optimality. Right? What it say? Principle of optimality. It say that look, if I want to get from any node to my goal node, and I already know that C to B is already optimal. Yeah, from node, any node, intermediates is C, right? The goal node is B, right? So I know that from C to B is already optimal. Okay, in this case, I call this minimum cost, right? That's why we call this SC, right? Okay, so I call this optimal. Pen. Okay. So I don't know that value, but I already know that this is optimal. Okay. I don't know that value of SC. What is SC? Cost, minimum cost, that is already optimal from C to the goal node. Okay. SD is the minimum cost from D to the goal node, B. I don't know that value, but I know this is already optimal. Right? So then I need to know from A to the goal node. This is my goal, right? I want to know from A to B, right? So in that case, all I need to do is, look, I don't care how I will get from D to B at this point. Okay? All I care is the one I have my problem right now, which is in A. All right. So what is in A? In A, I know only have two possibility. Okay, to go to C or to go to D. Right? To go to C, the cost is 1. To go to D, the cost is 0. Then SA is the minimum between 1 plus SC or 0 plus SD. Is that correct or not? My question,
Yes.
you have this kind of problem, can you formulate it similarly?
Hopefully, because it's similar to like life problem, right? You need to choose which one is like the fast or which one is like the cheapest. So yeah,
Yes.
hopefully we can.
Okay. Hopefully you can. Okay. So let's go a little bit further. So this is based on what is called principle of optimality again. Yeah? So the best path from A to B has property that whatever the initial decision at A, the remaining path to B, starting from the next point after A, which is C or D, would be the best path, right? Okay, the best path from A. So that's why we have this value. Next, okay, what is next? Now, I don't know earlier, right, about SC and SD. Okay, Now we will go to a point C now. Now in stage 2. Okay, so this is stage 1, this is stage 2. Now I'm in stage 2 now. Okay, what? In stage 2 now I'm in node C. To go to node B, the goal, how to do?
We have to choose between the minimum, between the, we use 5 to go to SE, or we use 4 to go to SF.
Correct, 4 plus SF, right? So 4 is the weight CF, right? And then SF, if something that we know that is already optimal, okay, we assume first that this is already optimal. Okay, we don't know that SF, we don't know that SE, but we know that this is already optimal. Okay, the same thing with D. Okay, now you are in point D, okay, in node D. What is the possible alternative? Of course, F and G, right? So then what is DF? 7. What is DG? 3. That's why you have this formula. Livy, can you get this formula or not?
Yeah, I got it.
Oh, you got it. Joy, no problem. Huh?
No problem.
No problem. Okay, if you are no problem, can you give me formula in node E? Joy. And then Livy, can you give me formula in node F?
Okay, for so SE equals to
Yes, SE equal to?
minimum either between 2 plus SH or 1 plus SI.
Wow, very good. How about Livy? I cannot hear you. Can you unmute?
Oh, sorry. So 1 plus SI and 2 plus SG.
Correct. So SF is equal to, yeah, okay, 1 plus SI and 2 plus SJ. The same thing, yeah. SG is 5 plus SJ plus 4 plus SK, right? So easy, right? Actually.
Yeah, I have a question, sir.
Oh, go.
Can we eliminate, like, for example, we have FF and SG, right? So we have 2 plus SG and 5 plus SJ. Wait, sorry, 2 plus SJ and 5 plus SJ
No,
in SF. Can we
F,
eliminate?
you
Like,
don't
just,
eliminate because
oh,
at
we
this
don't
point you
eliminate.
don't eliminate yet.
Okay, okay.
You just write down the formula because they are not the same, right?
Oh, okay, okay. Yeah.
You just write down the formula. All you need to do is write down the formula. This is called forward. You see, forward means from A to B, from the initial value to the goal state. Yeah? Later we will eliminate. Okay. The way to do in dynamic programming is you go first here. Okay, forward state first, and then the same, yeah. In state, this is 1, 2, 3, 4, right? So in state 4, you calculate the SH, SI, SJ, SK, right? No problem. The same thing in state 5. Okay, this is state 5. Here you have SL, SM, SN, right? SL has no other choice, only one choice. So 5 plus SO, right? In M, you have two possible choice, with this O and P. In N, you have only one way, with this 4 plus SP. Correct? Is it okay or not? Here, stage 5. Okay, now again, I want you to, Joy, can you give me SO? And Livy, can you give me SP? Stage 6.
That's always only 2.
2 plus
2 plus
SO equal SO equal 2 plus.
Oh, SO. 2 plus. Wait, if S also we're going to O, right? Why am I doing
Yeah,
this?
suppose you are already in O, okay?
Oh, already in O.
Yeah, suppose you are already in O, okay? So what is the formula SO? SO equal to minimum of what? What, Livy? SP, Livy.
1 plus SP.
Yes, so
Oh, plus.
SP is
We need to
the
add the.
minimum, yeah, of 1 plus SP. Okay, so that one. Okay. Now suppose you are in SB in the last part. What is the formula of SB? What is the formula of SB?
0.
Zero. Correct. Because, right, this is the gold node, so there is no other. Oh, SP is already zero, right? So what to do? We already know SP is zero. So, and then you go back here. Oh, I know SP is zero. Can I calculate SO and SP? Yes. Right? If I already know SO and SP, can I go back here? Can SO and SP is already given, right? So can I calculate SL, SM, SN? Yes. Right? And then go back again. Oh, SL, SM, SN already given. So can I calculate SH, SI, SJ, SK? Yes. Okay. The same thing. So this is the backward computation. Okay, so at state 6, you already know SO and SP, and then come back again to stage 5, right? And then come back again to state 4, and then come back to state 3, and come back to state 2, and finally go back to stage 1 to reach the origin. And then you will ask, okay, what is the shortest path in here? Oh, the one that give you the minimum. That is the shortest path, right? In every state. So here in state 6, okay, this is of course SP is the shortest path. And then in state 6, what is this? Between SO and SP, which one? In O, yeah, on itself, okay? So then here, okay, you see in SL is clear, SN is clear, but SM, you have two choices, right? Via O or via P. So, and then you will see in SM here, what is the minimum? The minimum is 4. Where it come from? It come from 2 plus SO. That means it will go from O, okay? So link OM is the one that we will use as the path if M is chosen. Okay, the same thing here. Okay, so you will check which one is the minimum. Okay, so SI here, which one is the minimum? SI is the SI is equal to 8. Where it come from?
From SM.
Yes, from SM. Okay, so in that case, MI will be the link. If use I, mi will be the link. Okay, and so on. The same thing here, right? So then you can find that shortest path. Okay, so you check the red box that is in the backward computation earlier. So in stage A, you know the minimum is 13. Again, minimum 13 is from where? Through C, right? Okay. If through D, it will give you 14. But if through C, it will give you 13. So in that case, A going to C, right? And then from C here, so you check in C, okay? If I pass through E, it will give me 14. If I pass through F, it will give me 12. So then I will choose F. Okay, and so on. Can you see that or not? So you can calculate the minimum cost, which is 13 in this case. Okay, and then you can also find the shortest path. Okay, this is the example. So next one is of course your practice. Okay. So now before that practice, okay, I want you to check the efficiency of the computation. Yeah. Compare the number of computation, the addition and comparison by brute force, right? Compared to the dynamic programming. Okay. If you use brute force, okay, look, we have n is the number of stages. The number of paths depending on either up or down, right? So because in here is clearly only 2, up and down only. So then it's combinatoric of n and n divided by 2. Okay, so this is the formula of combination. So n is 6. In that case, the number of paths is 20, right? But if you look at the number of addition and the number of comparison, this is the formula. Okay. Now, if you use the brute force computation, okay, for n equals 6 number of states, yeah? So you have 20 distinct paths from A to B, consists of 5 addition on each path and 1 comparison to get the minimum per path, okay, except the last, right? So in that case, the number of computation become 20 multiplied by 5, okay, plus 19. That is the number of computation in brute force. So 119. Okay. Now, the dynamic programming in comparison, okay, for n state, the number of addition and comparison is using this formula. Okay. You will see that we have only 24 plus 9, which is 33 computation. Okay. So 33 compared to 119. Okay. So much efficient using. So how about if you have n equal 20 stages? Can you compare the brute force and dynamic programming? Oh. So who will do the brute force and who will do the dynamic programming? One of you will do the brute force computation and one of you will use the dynamic programming. You can choose which one. First come, first in. Joy, which one you will choose?
I will the
Or DP?
the dynamic programming.
Okay. Okay. Joy will compute the dynamic programming. Livy, you compute the brute force. Okay. N equal 20. Earlier I give you example n equals 6, right? So if n equal 20, what is the number of computation?
Similar, that's why.
Actually, not the same. Critical path method is not the same as TP. So this is another method.
Okay.
Critical path method is used to get the longest, right? The longest path. This one is the shortest path,
Okay. Okay.
right? CPM is used to find the longest path. In the scheduling, right? You want to find the longest path.
Yeah.
Yes. So in the schedule, that is called critical path. Okay. So in DP, in here, you want to find the minimum, the shortest path. But in fact, DP itself, okay, is not the best way to calculate the shortest path. At this time, the shortest path algorithm that is the best is called Dijkstra.
Check. How do you spell it out?
Okay,
DJ.
I will find it. Dijkstra, Dijkstra algorithm. The best shortest path algorithm at this point that I know. Okay, I don't know every day. Probably there is a new one, but the best one is Dijkstra at this point.
Oh, we actually learned this last semester.
Okay, which
Dijkstra.
which course did you learn this?
Operation research one.
Okay, so
But fast because we learned it also with like Floyd, I think the name.
Floyd also you learn that is to get the maximum flow.
Yeah, but it gets really confusing because like once you lost your like focus, you're gone. In like because I use Excel, right, to like note
Yes,
everything. So it
I
gets
see.
confusing. It's only numbers and like permanent, temporary, and that's it.
I see. So anyway, there are many sources for Dijkstra algorithm. Which Floyd do you use? Floyd Warshall or
I don't quite know, but we use like D1 and S1. Wait, I can show it to you. I still have the
okay,
file.
okay. Maybe that is Floyd Warshall. That is okay. This is Floyd Warshall.
Okay.
Okay, so this Floyd Warshall is to get shortest path from any node to any other node.
Oh yeah.
Okay, Dijkstra is to get the shortest path from one node, not any, one node to one destination.
Oh, now
Okay,
that makes. Oh yeah.
that is different. So Dijkstra is to get from one initial node to one destination. What Floyd Warshall is to get from all node to all other node. So many to many is one to one. DP is the same as Dijkstra, but DP, the interesting in DP is actually the principle of optimality itself, right? So in terms of algorithm, is not as good as Dijkstra, okay? But clearly this help. Say for example, Dijkstra is only for shortest path, right? But DP you can use for any other problem. Okay? For example, source allocation, knapsack. Later we will discuss knapsack. Okay, so Livy, what is the brute force?
Oh, the combination we take it from the n, right? No,
Yeah, n and then
for
n.
the combination. Yeah, so the n weight is very big.
Very big, right?
Yeah, it's like 6.7 multiplied by 10 to the power of 10.
Yeah, very big. Oh, no. N is 20 and then n divided by 2 is 10, right?
Yeah.
Right. So that one is like 184,000 only. 184,756. Right? Let me check in Excel. Kongbin. Kongbin of 2010. Oh, in Excel is Kongbin 2010. That is 184,756. There. Right? And then multiply this with, okay, I will put 20, right? And then this one is 20 divided by 2. Right? So this is the input. Okay. And then, so you will say, this is the number of computation is Kongbin of this number, and the number of chosen is 10. Okay, and then multiply this by n minus 1. This one minus 1, that is 19. So multiply 19 multiplied by, so this is a kind of how many? Million, right? 3 million. 3 million.
So yeah.
Okay.
So
The number of addition is 3 million. The number of comparison. The number of comparison is this one minus 1. So this one minus 1. Okay. So it's only 185, right? 84. So 184,755, yeah? And 3 million. So this is the result. Okay. So yes, of course, compared to earlier, if we use DP, okay, if you use DP, that one is 20 exponent 2, right? And then this one divided by 2, 200, and then plus n, right? Plus n is 20. So become 220 for addition. Okay, the number of comparison is n square, again the same, divided by 4. This one divided by 4 is only 100. So the total is this one plus this one is 320. Well, if you use brute force, this one divided plus this one. So this is the, if you can compare, okay, I will put the blue compared to blue. So using DP, you need only 320, but using brute force, you need 3,695,119. Okay, so that is how efficient is dynamic programming compared to brute force for this problem. Is it clear or not? Okay. Any question? Any question? So let's do it again. Okay. Using DP to compute the shortest path. Okay, so you specify the node origin and node destination, right? That is given. And then you check the destination node and then compute the minimum cost among all incoming arrow. Okay, important here, incoming arrow. Okay. to that node. Okay, incoming, all incoming arrow to the node that do not make any cycle. So do not make any cycle to computation. And then follow the node in the minimum cost computation until the node origin. Earlier, the same. You can calculate Sx. What is Sx here? Is the total minimum cost from the node origin to node X. Okay. So to maintain the no cycle, you keep the list of node that has been included in the equation. Okay, so I give you example here. Find the shortest path from node 4 to node 1. So I'm using forward computation here first, right? So from node 4 here, okay, to node 1 here. So this is the initial init, okay, and this is the goal. Okay, so how to get that? So node 1, right? The goal is node 1, so then you check to go to node 1, what is the incoming arrow? Okay, that is incoming is only from node 2, right? So S1 equal to S2 plus 20. This is more complex than earlier example, right? Why? Because outgoing arrow you don't need to care. Okay, only the incoming arrow. Now you are in node 2. Okay, in node 2, what is the incoming arrow to node 2? Can you check? The incoming arrow to node 2 is from node 1, from node 3, and from node 5. Can you see it or not? From node 1, the cost is 20. From node 5, the cost is 15. And then from node 3, the cost is again 15. Right? So, but we already know, okay, that S1 plus 20 will create a cycle, right? If we put that. So in that case, we remove. Okay. So S1 plus 20 is removed. Why? Because if we include that, it will come back to node 1. So it's already S1 plus S1 is already included. So then we remove from the equation. Okay. And then next is node 3. From what is the incoming arrow to node 3? S1 plus 25 and then S2 plus 15. Yeah. Incoming arrow is from node 1 and node 2. Okay. But node 1 and node 2 is already there. We already mentioned, right? So that one means this is, if we include that, it will create cycle. That's why no need to include. So, okay. And then what? Next is node 5. What is the incoming arrow to node 5? Okay. From node 3 and node 4. Can you see it? Okay. What is the cost? Is 10 and 10, right? So then we see that node 3 is already mentioned, right? So then we remove. Okay. And then last one is node 4. But this is the origin. So S4 is 0. And then now we do backward. So computation. Okay, that is easy. Just put it back. Okay, S5 equal to S4 plus 10, S2 equal to the minimum of this. Okay. And then finally you get F1 is 45. And you can get the node sequence. Okay, up to here. Is there any question? Trying to understand. Do you get it or not? Probably you don't get it. Why we need to remove? Is that so? So you start from the goal node, right? In this case, the goal node is node 1. Okay. You keep record on the node that you already visited. Okay. Because if the node is already visited, you remove from the equation. So in node 1, okay, to go to node 1, the only way is through node 2, right? So then we have S1 equal S2 plus 20. 20 is the cost from node 2 to node 1. And then from node 2, you have 3 ways. Yeah? One is through node 1, node 2, and node 3, and node 5. Can you see the drawing or not? Right? But node 1 is already visited. That's why you remove from the equation. Okay? The same thing with node 3. Okay? S3 here, incoming arrow is 1 and 2, right? But again, node 1 and node 2 is already visited. So then you don't use that. So you remove. Okay? Next is node 5. Okay? Again, node 3 is already visited. So you remove. Right? The last one is node origin. Okay? Once you create all this forward algorithm, the next state is backward. That easy. Right? It's just plug in the numbers. Okay, so practice, okay, practice. Okay, without looking, this is the answer already, right? Without looking, can you find the shortest path from node 4 to node 1? And then the next practice, can you find the shortest path from node 1 to node 5? Oh, the same value. Okay, so one each, okay? Which one? Node 4 to node 1 and from node 1 to node 5. We have two problems. One for each of you. You choose. Livy, you choose first this time. 1 to 5 or 4 to 1. You will calculate the whiteboard.
So we do like forward and backward.
Yep, both. You do it in one.
So
Which
I
one?
choose 1 to 5.
Okay, 1 to 5. Good.
Yeah.
Okay. So while you are doing it, okay, I will pause the recording. Okay, so your turn to show your.
Okay, I will join the Zoom through my phone so I can share
Yes.
screen. Right. Mm.
share your screen. Mhm. Okay, can you explain?
Yeah, so I need to find the shortest path from node 1 to node 5. So we start from node 5.
Mhm.
From node 5, we we are looking for the node that is coincide to the node 5. So that are node 4 and also node 3. So node 3 is S3 plus 10 and S4 plus 10.
Mhm.
And then after that, we go to node 4. And then the one that go to the node 4 is the node 2 and also node 5.
Correct.
And for node 2 is S2 plus 20 and S5 plus 10.
Mhm.
Because if we choose F5, it goes back to the node 5. We eliminated the S5
Very good.
and then we move to the node 3, and then we looking for the link that is go inside to the number the node 3,
Correct.
and then we found the S1 plus
Mhm.
25 and also S2 plus 15.
Mhm.
And then we go to the node 2. We, it's same. We are looking for the minimum node, the minimum value of the node. So the first one is S1 plus 20, S3
Mhm.
plus 15, and
Mhm.
S5 plus 15.
Mhm.
So we eliminated the S3 and S5 because it will go back to uh,
The one that.
yeah, the original node.
Yes.
And for the node 1, it's the origin, so the S1 is 0.
Okay.
And then we do the traceback. The traceback, we start this, we go first to the node 2, and
Mhm.
then in the node 2, we got S1 plus 20,
Mhm.
where S1 is 0, so we got the S2 is 20.
Mhm.
And then the S3, we select the S1 plus 25. The
Mhm.
S1 is 0, so we got 25 for S3. And then for S4, we select between S2 plus 20 and also S5 plus 10.
Mhm.
We don't have the S5, so we choose the S2. So as the S2 is 20 plus 20, so we got 40.
Mhm.
And then the last is S5.
Mhm.
We choose between S3 plus 10 and also S4 plus 10. We choose between the S3 and S4, the minimum, the one that has the minimum value is S3, so we choose S3, which is 25 plus
Mhm.
10, so we got 35.
Okay. 35 is the answer, and then the node sequence is 135. Okay. My question: why S5? In S4, why the S5 plus 10 you remove?
Because I just like eliminate it because we still don't know the value of S5.
I think because in the forward earlier, okay, you already put there S5 earlier. This one. Where is the annotation? You cannot annotate. Oh. This part in Note 5 in the you already have a Note 5 annotation. Why we cannot annotate? Because this is in so in the forward. right? You already have node 5. Can you see?
Mhm.
And then after node 5, you go to node 4, right? When you put node 4 here, it consists of node 5 and node 2, correct?
Yeah.
But node 5 is already mentioned earlier, is already visited. So in this case, you need to remove the node 5.
Oh.
Right. Yes. Okay, so your answer is correct. So I hope you really understand. Okay, so Joy,
Yeah.
can you share your screen?
Okay, wait.
Excellent, Livy. Yeah.
Thank you, sir.
Hmm.
Okay, did it in Excel.
Oh, sure.
So my goal was to go to 1 from 4. So in note, so
One
we
to
start with the goal. So note
from 1 to
4
4.
to 4 to 1.
4 to 1. Okay.
Yeah, so we start with 1. As
Okay.
you can see here, the only one going to 1 is from S2. So S2 plus
Right.
20. Then we go to note 2, right?
Mm-hmm.
We actually have several notes going to S2, but then I for the ones we already visit, I put red. And S3 I will explain later. I put red
Mm-hmm.
for S1. Cannot use that because we're going to there. Then we have S3 15 and we have S5 plus 15.
Yes.
Then we go to node 3. We have S1 plus 25, S2 plus 15. But we visited those nodes already. So I put
Yes.
the red one. Means
Okay. It's already
uh
stated.
yeah, we cannot go there. So
Mm-hmm.
then we have node 5.
Mm-hmm.
Because we cannot go to node 4 because node 4 is our starting point, right? So we go to node 5 first. And we have S3 and but then we already visit S3. So cannot. So I put red again.
Mm-hmm.
Then then we found the node 4 to start,
Right.
which is 0. Then we start to backtrack.
Okay.
I put the ones that we choose. So we choose S4 because we cannot go to S3 because if you see later S3 it's both red, which means we cannot go there. So I pick S4. So 0 plus 10. So it's 10. Then
Mm-hmm.
we go up. We want to go to S3, but then we see, oh no, we went to S3 is red,
Already.
so we cannot go
Right.
that. So we go to S2. Then we can find that S5 actually, we can go from S5. So we choose S5. That's why I put it. So now it's 25. This one I highlight the S3 as red because we cannot go to S3.
Yes.
Okay, then we just go to our final goal, S1.
Mm-hmm.
So S2 plus 20, S2 is 25. So 25 plus 20, 45.
Mm-hmm.
Yeah. So the result is 45.
Right. And then the sequence.
The sequence is S4, S5, S2, and S1.
Okay. Excellent. Excellent. So the challenge is actually to create a Python program based on your computation, right? Because how are you going to remove the one that you already visited? That's the point. I think it's a good assignment, right? But I already posted a different assignment anyway about knapsack using dynamic programming also. Okay. Okay. Let's go to knapsack problem. So aside from shortest path, we can also solve knapsack problem using dynamic programming. Okay, this is knapsack we discussed last week, right? Remember during the integer programming. Okay, so say you want to load a truck with three types of items. Okay, each unit item has weight. For example, 2, 3, and 1. Okay? And then maximum cargo weight is just 5. So So the question is assign the most valuable item without exceeding the max cargo. Can you solve it? Okay. So this problem is from our handbook, which is from Taha, right? So we have discussed last meeting that general optimization of knapsack is something like this. So you need to maximize, okay, the x times v1. What is xi? Xi is the number of units of the items, I. Okay, v1, v1, v2, v3 until vn is the value. That is like the benefit, subject to constraint of the cost. Okay, x1 times w1, that means the number of items 1 multiplied by the cost or the weight of item 1 and so on. Yeah? We add all of this, must be less than a certain capacity of your knapsack, okay, W. Okay? And this is integer problem, so xi must be integer. So of course you can use simplex method, okay, but xi is non-negative integer. So we can also use DP, dynamic programming. So this is like another way. Okay. Let's discuss the terminology first. Okay. In dynamic programming, we have states and state, right? The states represented by the items. So we have n items. And then the state or the node, yeah, the state is represented by the node. So let's call this node yj. Okay, is the total weight assigned to states I to n. Yeah? And then there is a boundary, which is the capacity. Yeah? In this case, the capacity, let's say the y1 later on, this is our goal, will be equal to w, right? And then this is something that you want to know. So the alternative is the one that you want to know. So the decision variables xj, yeah, at state j is the number of units of item j. Okay. So how many items we have in this problem? 3. Yeah. So we have 3 stages because the number of items is only 3. Okay. And for each item, there are how many possible value? For each item, because this is discrete, so how many possible value? Say item 1. What is the possible value of item 1? If you want to talk, can you unmute? How many possible value of item 1? How many possible? How many possible value of item 1, item 2, item 3? You get? You still remember knapsack? Yes or no? Last week. I cannot hear you.
Yes.
Okay. So, what is knapsack problem? Can you brief me?
Like the definition.
Yeah. What is the problem in your mind? What is knapsack problem? What is the problem? So what is given? What is the output? What is input? What is output?
The input should be the cost, right?
The input.
Cost.
The input is this table. So there is cost and benefit. Yeah?
So
Cost is the weight. The value is the benefit. And then one more input. What is the next input that is important there?
Limitation.
Correct. The limitation, that is the maximum cargo weight here, is the capacity of the knapsack. So you want to go to the mountain, remember the story. You want to go to the mountain, okay, you want to bring certain items that is valuable to you. So for each item you put value, right? And then each item also have certain weight, okay, 1 kilo, 2 kilo, and so on, right? And then you want to maximize the value in order so that the amount of items in your knapsack will be less than certain capacity that you can carry. Okay, so now we want to use dynamic programming. Okay, so able to use dynamic programming, we need to define two things first: states and states. The state is the node. Okay, that is xj, x, the value of x, the alternative. Then the stages, okay, is the step to compute. Okay, so I said here, okay, the state j is represented by the items. So you have how many items? In here you have 3 items, right? Okay, item 1, item 2, item 3. So in this case, n is 3. Okay, and then we have w in here is the boundary, which is, what is this in here? 5. Okay, that is the number of cargo weight that you can get. Now the question is this. Now you need to create the node, right? Okay, to get the node, you need to know how many alternative, what are the possible value for item 1, or say I call this item A, B, C, so that you will. So this is equal A, yeah? This is B, okay? So that is C. So item A, B, and C, okay? Or item 1, 2, 3, okay? So my question, for item A, what are the possible values? Can A be 0? Meaning you
Yeah.
bring? Yes. What is the maximum of XA?
Um, the value is 65.
No, that's the
It's
value. I mean, the,
the weight. So
no. Our goal is to find how many items can you, how many units of item
oh,
can you bring, right? Correct?
mm,
How many units of item A can you bring? Per unit, the value is 65. So that the number of units of item I is xi. Okay, this is what you want to know. So because this is discrete, correct? So you need to find out what are the possible value of that discrete values. What are the possible units? 0 is clear, right? 1, can item A be 1?
yeah.
Can item A be 2? Yeah, right? So what is the maximum of number of unit of item A that we can put?
You can bring 2.
Yeah, you can bring 2. Can you bring 5?
Cannot.
Why not? Its maximum cargo is 5, so can, right? Meaning B0, C0, possible? Only A, for example, you bring. Possible, right?
Yes.
That's the feasible value. Can A be 6?
No.
Why?
Overweight.
Correct. So that means the value of XA or X1 is only 0, 1, 2, 3, 4, 5. So 6 values. Correct?
Hmm.
Can you get it? So that is how you will do. Okay. Here. For item Xi or X1, so you have 0 to 5. Yeah? X2, you will have 0 to 5, right? And then for item 3 or item C, you have 0 to 5. Can you see that? And then, of course, the link here is just the sequence. Okay. And then you know the value is 65, 80, and 30. Can you reverse? For example, 30 is item A rather than item C. Possible, right? So the order does not matter in this case. Yeah. So go back again, yeah. So we have item N is 3, W is 5. Okay. So the first thing you need to do is to define what is called optimal value of the state J until state N, right? Given the state node Yj. Okay. So then you need to define the formula. Okay. So in this case, the formula is rather simple. Okay. At the end, Fn is this. In this case, earlier shortest path, that's minimized. Right? In this case, you want to maximize. What do you want to maximize? You want to maximize in each decision. Okay. Xn times Vn. Okay. In this case, n is 3, right? So, and then this is the floor function. The x is between 0 until the number of yj divided by wj. Yeah, this is the floor function. And then the recursive formula is above. Can you see it here? The recursive formula, okay, it's that value itself, okay, and then the value in front. Okay, so look at the Fj. It depends on the value. This is the weight. The one that I encircle is the weight, right? And then the value in front. Okay. So the value of Yj minus Xj times Yj. Okay. So using this, okay, the maximum feasible value of Xj is based on the floor function. Yeah, this is the floor function. Okay. Now, and you can delete all infeasible alternative given the value of Yj. Let's take the example in this case. Okay. This is our value. You have item 1, 2, 3 or A, B, C, right? So we start with stage 3. Okay. So stage 3 is item 3 here, right? The value is 30. So you put 30 times x3, right? So, and then what we want to maximize x3, okay, which is w divided by w3. W3 is 1, right? So w is 5. So the maximum of x3 is 5. Okay. Then in state 3, we start to create a table. Why? Because so many, right? So you have possible value is 0 to 5. Okay. So this is the y. Huh? Now we want to get the value of 30 times x3. Okay. So x3 can be what? Can be 0 to 5 also, right? So then we create this. So we multiply, okay, x3 times v3. Huh? So, so you will get what? 0, 30, 60, 90, 120, 150, right? Do you know how to get this, right? This is the x3 multiplied by 30. Okay? So, then you check that this is not supposed to go beyond that. So, then you create this table. Okay? You can calculate the F3. Okay, F3Y3, which is maximum of 30 times X3. Okay, so what is the maximum X3 times 30? Okay, so you will get 0, okay, 30, 60, and up to 150, right? So in that case, what is that X that make it maximum? Okay, so here the maximum is 30, right? Here the maximum is 60. Here the maximum is 90, the maximum is 120, the maximum is 150 from where? There. From that X is 1. This one is X is 2, right? And so on. So this one is the result of X3 if, okay, if x3 is 0, this is the reward. If x3 is 1, this is the reward. And so on. Can you get this or not? You have any question up to here?
No, all clear, sir.
All clear. Very good. So next we go to the, okay. So we go to the next stage, okay? Stage 2. So we put the formula first, okay? Y2, F2, Y2 is maximum of X2, okay? What is this? This is the weight, yeah? That is 80 times X2 plus the earlier, right? From the formula earlier, so F3, Y2 minus 3 times X2. When you check the formula earlier, yeah, this is the formula earlier, right? This is the one that we use, okay? So then we can use again, so Yj minus Xj Wj. Yeah, so this is what we use. Okay, Yj is 2, this is also Xj, X2 also, right? So, and then we put it into this table, okay? Here we put it into this table, okay? So we put it into this table, we get this value, okay? So this is 0 plus 0, right? And so on. This one is x2 is actually 1, right? So of course 80 times 1 is 80, and so on. Okay. So and then we get the optimal value. Okay. We get the optimal value. This is the value, and this is the x. So the maximum is 1. Right? The maximum is 1. So in this case, the optimal value is 0. Yeah? This is the 0 is the maximum. This is the 30 is the 0. This is again, this is the maximum, right? Again, this is maximum, 90, right? And then 120 compared to 110, this is maximum. 150 140, 150 is maximum. Okay, so the x2 in this case is 0, all 0. Okay, this is the optimum value. And then we go to stage 1. Okay, we go to stage 1. Again, we put into formula like a while ago. Okay, so go back to the formula a while ago. Where is the formula? Yeah. So we use this formula again, but this one is now 1, y1. Okay, so using this formula. So we put it here. Okay, so f1 y1 maximum of 65 times x1. Okay, f2. Okay, this is the 1, so this is must be 2, right? One step earlier of y1 2 times x1. Again, the maximum is now 2. Okay, so then we put all this value into this table again so that you can do more systematically, right? So x1 0, 1, and 2. Maximum is 2, right? So we put all this value into this, and then we get the maximum, right? What is the maximum for each row? 0, 30, 65. This is wrong. This is 65. This is 65, and then 95, 130, and then 160. Right? When it happened? It happened when x is 0. X is 0 again. This is 65. So when x is 1, this is when x is 1. This happened when x is 2. This is happened when x is 2. So this one. Right? So then we go back. Right? In state 1, we already know that W1 should be equal to the Y1 equal to W, which is 5. Right? So Y1 is equal to W, which is 5. Then X1 become 2. Okay? So that here, the one that I put red box here. Okay? So we know that this is 5, so we become maximum is 2, optimal. The value is 5. And then what make it happen? This 30 that make it happen, right? So that is x equal to 2. Okay, and then we go to stage 2. Okay, again in stage 2 we have here the one that make it optimum is this one. Okay, so with x equals 0, x2 equals 0, and the value is 30, right? And then next, the last one is go back to stage 3 again. Okay, the value is x3 equal 1. Here, okay, with the reward equal 30 again. Okay, it happened when x equal 1. So then we have the path. Okay? So I just listed here the path of optimum solution. Yeah? Become x1, x2, x3. Now because this is optimum, we put star. Okay, so this one, right? 2, 0, and 1. Okay, and then the total value you just multiply. So you can check here the total cost. Okay, 2 times 2 is 4, right? And then 3 times 0 is 0. 1 times 1 is 1. The total is 5, which is equal or equal to W, when W is 5. And then here, the value is, what is this? 65 times 2, right? This is 80 times 2, and then this is 30 times 1. Okay, so we get 160. So we have the solution of knapsack using dynamic programming. So basically you just use this formula that we put earlier. There, well, this one. Okay. So is there any question?
I have a question, sir. So to
Okay.
a knapsack problem, we actually can have like multiple solutions sometimes.
Correct. That's correct. So one problem you can use many different methods.
Okay.
Okay. So TP is just one method. Okay. Uh, the good thing of TP, this is like generic method. Okay. Generic method that can solve many problems is not the best one. Like earlier, like shortest path, for example, you can use TP. Of course, it's reduced a lot. Okay. But at the same time, this is not the best algorithm. Yeah, the best algorithm is the extra. It is not TP. Right? But at the same time, it's a progress toward the best algorithm. So say, for example, you find a new problem, okay, that you cannot solve using any other algorithm. You probably want to consider, oh, in that case, I will use TP because this is a new problem that I cannot solve it using other technique. Then at least I can solve using dynamic programming. Okay, and if you compare, how you compare? You compare with brute force. Right. There are many books on dynamic programming that you can also learn on your own. In fact, the algorithm, for example, to calculate, oh, the float Marshall is actually based on DPU.
But Marshall is based on
Hmm?
But Marshall is based on what, sir? Can you
The
repeat?
dynamic, Fort Marshall is based on dynamic programming, right? The basic of Fort Marshall, the one that you showed a while ago.
Oh yeah, yeah. But they just use like metrics, right?
Yes. That is actually based on dynamic,
Mhm.
the formula behind. So this is like the basic behind many algorithms. So, okay, to make sure you can do it, so I want to give you the, so I posted in Lentera this assignment. Oh, the solution a while ago. Okay, the solution a while ago is the same as this network, right? And then you just highlight the network. So 201, that is the actual DB solution of this, right? 201. Can you see? Where is that? Oh, this one. So this is 2, right? 0, 1. That is exactly the same as this one. 201. So knapsack. Now you can relate knapsack with shortest path. It's just for completeness. At least you know. Oh, this the same problem. I can view it different way. So up to here, is there any question? And this is your assignment. Okay. Exactly knapsack. So please solve it using dynamic programming. It's up to you. You want to use Excel, you want to use Python. It's up to you. Yeah. So here you want to hike and you can carry 9 kilo. Okay. It's discrete, so the possible value is 0, 1, 2, 3 until 9. Okay. And you have 5 items A to E. If you go to Lentera, you need to go to the right. You need to slide to the right to get this value because it's very long to the right. So anyway, the value is already in the slide, okay, of the weight and values. Dynamic programming. Okay, I need to save. Okay. Shall we go to the next topic? Decision analysis. But before that, do you have any question about dynamic programming?
Right now, no.
No. Livy, surely you are clear or
I have one question.
oh,
Like,
go.
wait. The dynamic programming is not the same as the linear and integer programming. Right? Like
It's not the same.
not,
It's not the same.
because the last week we discussed the integer programming and also the linear programming. It's a bit similar, right?
Correct. It's a bit similar. Actually, during integer programming, I did not discuss the detail on the algorithm integer programming, right?
Hmm.
Right. I just
Yeah.
the solver. That's why you feel it similar.
Oh.
Okay. So the detail of integer programming is this: dynamic programming. When you see the detail, they are not the same.
Mm.
In linear programming, you can put graphically, right, and then you draw a line to create a boundary, right? In discrete or integer programming, you don't draw that line. You actually find all the combination or all the permutation, right? Depending on the problems, right? So that's why it's become exponentially explosive. And dynamic programming is just one of the technique of the algorithm behind that solver.
Mm.
You got it.
Yeah. Got it now.
So on the surface, yes, they look like the same, just discrete and continuous, right? You just click, click, click. So, right? And then it's the same, right? Yes. It's look like the same. But when you go inside the detail, they are totally different, isn't it? Now, uh, now you see when we study dynamic programming, you start to see, hey, now I need to enumerate, right? A while ago, you enumerate
Mhm.
1, 2, 3, right? You enumerate all possible values, correct?
Yeah.
Yeah, and then you find optimum value of that enumeration.
Mm.
The detail is not the same. Okay, so
Mhm.
programming is related to integer programming in a way that actually dynamic programming is the algorithm behind. Okay,
Oh.
okay, you got it. So of course many, yeah. Branch and bound, for example, is another technique, right? But we don't discuss it here.
Mm.
So there are many techniques to do integer programming. Okay? In 3 courses, you cannot finish this unless you are really doing operation research course 5 years. You will study each of the algorithm. So I don't think it is worth for you. Okay, but at the same time, we just touch the surface here. Okay, at least you know. Okay, you get the sense, right? Oh, okay. This is different problem, and this is actually behind. Okay, this is actually the algorithm behind that problem. So
Mm.
at least in the global sense, you already know uh, where you are, okay, in the optimization. Uh, go to Lentera, next meeting, you're supposed to give me your presentation. Is that correct?
Yeah.
Yes. So, yes. So, March 8th is the first presentation. So, you submitted the progress report. Okay. What will be your project idea, your problems? Okay. And then what analysis you want to do. This is just proposal. Right? So in the beginning of next meeting, you will do a progress report of the project. Okay, so is there any other question regarding the integer programming and linear programming calculus up to DP? Am I too fast or too slow? I don't know. Or just okay?
It's
Sir, I
okay.
have one question
Go,
again.
go.
Last question. So, is there any like a specific requirement that we need to be concerned to use the dynamic programming?
No, you should know the dynamic programming is when you have enumeration, discrete enumeration,
Oh.
okay, very large, and then you want to reduce that combination.
Mm.
So then use dynamic programming.
Mm.
Yeah, your question is very good. So you want to know when should I apply dynamic programming? That's what you ask, right? Then
Yeah.
you check, is there any discrete enumeration, very big, that you want to reduce the number of computation? Okay. How do you reduce? Again, based on the principle of optimality, right? Then you ask, what is principle of optimality? Okay. Oh, principle of optimality means if I know or you assume that from intermediate node to the goal node is already optimal, right?
Mhm.
Then I can go from any other from here to the optimal one. Okay, just one step behind become optimal, and then you put forward and backward. What you did a while ago today, right? The one that you use for the spot. Okay? The same thing in knapsack, we do the same thing, right? We do forward, we do backward. Okay? The formula is different, but the technique is the same. What make it the same is the principle of optimality. So,
Okay.
in the sense that you can apply for any problem. Okay, with this discrete. If you read the book of Bellman, he is not just applied to discrete. Yeah, he even applied to continuous function, also integration,
Mhm.
and so on. So very complex problem that he solved. Okay. Joy, you want to say something a while ago? Sorry.
No, no, all good.
Okay. Okay. So, and is there any other question or discussion if you want to discuss something?
Oh, I just want to ask about the project itself.
Go.
So we need to use any software to help analyze.
You can use any software. Okay. So you can use Excel. You can use what is that? The one that we used last time.
What are your expectations?
Oh, I believe you go beyond my expectation as usual. So
Because for operation research, it's like a quite broad topic. What I was thinking of was like there's this research about like stochastic uh stochastic dynamic programming for Wordle. Do you know Wordle?
Mm-hmm.
But it would be quite complex, so I don't know if I can finish it. And there's also like the normal operation research project where you optimize for a company.
Correct.
So like, which one do you like prefer us to do? So like I
Yeah,
can know
I
what
think
your
I think if you can, for example, uh, just the normal for any company, and then you create the most important is to create the optimization problems. The formula is either minimize, maximize, right? And then what is the objective, right? And then what is the constraint, okay? And then you start to solve that one, and then you create a program to solve that if possible, you create a program to solve that. Say, for example, simple knapsack like this, or a simple, what is this called? Shortest path, right? And then you apply this simple problem to a real industry problem that you actually have it. And then at the same time, you say create a Python program to solve that so that it can be used for general purpose, for example, not just for that particular problem at hand today, but probably also for the future. Oh, that's more than enough,
okay.
right? Because that means you can generalize already, even if very specific for that particular type of problem. That is very excellent already.
Okay. Okay, thank you, sir.
Yeah. So I, if you want to create the stochastic one, that is fine. But I think the theory behind we don't discuss it here, right? Oh, I discuss a little bit stochastic at the end about my research, which is also similar, right? So when we talk about Markov chains and until I have n, yeah. But at the same time, that is I don't expect much from you from that topic, okay? Because it's probably too advanced. Okay, so let's go to the one more thing before that. Decision making. If possible, your project is about decision making. Okay, it's not just optimization, but it's also about decision making. So in the next few weeks, okay, many weeks actually, we will discuss decision making, okay, including how you will make decision, okay, up to game theory. Okay, before that, did you learn decision analysis in other course or game theory in other courses?
We learned game theory and economics.
Oh, you already have economics. So what did you learn in game theory and economics?
It was really brief, so I don't quite remember.
Okay. Uh,
It's like the prisoner's. Wait, is it the same with the prisoner's dilemma?
Personal dilemma you already learned.
Yeah, that's the only thing I remember.
Okay. So you know how to compute.
I don't think. I don't know. Maybe. I
Maybe.
forgot.
Okay, we will repeat again in that case. Okay, and you tell me if this is too slow. I can make it faster, and then I can go a little bit more advanced. But at the same time, if this is because I don't know what is your need, so you need to tell me. Okay. Okay, let's go to decision analysis today. This is like the beginning. So you can follow this slide in Lantera. So this is a new topic, okay? Decision analysis. So first slide is about how people make decision. So first thing, the most important in this slide is about what is decision, okay? And then next question is when do you need decision analysis, right? and I will touch a little bit about classical decision analysis strategy. Okay, and we talk about destiny versus decision. So, can you give example of important decision that you did recently? And did you use decision analysis for that decision? And if not, so how do you decide? What strategy did you use? Okay, tell me first. What decision did you make recently? Hmm. Joy,
An important one.
up to you. I don't know.
So I decided to take my TOEFL without studying.
Wow.
Yeah.
So the decision is to take TOEFL. Then,
And I think I don't quite use decision analysis. It's more of like I don't have any more decision to make because I need the result by a week, and my test is like still March 3rd, and I need it by March 10th.
wow. Where are you going to planning to study for that TOEFL?
I don't know. I don't have time. That's why.
Okay. So,
Yeah.
so what strategy? How do you decide?
How I decide on like facing the test later.
Hmm.
My strategy is to attempt like several simulation of the test itself. And
Okay.
if I get a score, a pretty score of higher than 90
Mm-hmm.
over 100, then I will like take the test calmly. But then if I get below 90, then I think I need to like either postpone the test or I need to study harder. Like,
Okay. So you will repeat again.
yes,
So how important is that decision for you?
very important because the test is not cheap as well, right? It's quite like $200 once.
Oh, now it's $200.
Yeah,
Wow. Before $100, now 200.
yeah. Price increase.
The inflation is so big. Livy, what example of decision that you did recently?
Um, may, mm,
Maybe what?
maybe when I like buy like like a hand machine for like uh yeah do my hobby. So it's
Okay.
quite expensive actually.
Okay. Expensive.
Um,
And did you use decision analysis for that decision? So if not, how do you?
yeah, I think yeah because at first I like oh I need to choose the like the type the series that I want to buy
Mm-hmm.
because it has many choices with
Mm-hmm.
different feature. So yeah,
Okay.
I need to consider it with my own need.
Mm-hmm.
Yes. So
So
yeah, so I like the
aside from the
middle
type
one.
and series, what else?
Mm, the price, like, is it
Price.
worth the feature worth the price?
Okay.
And then is it very different from the lower feature or not?
Okay.
Yeah.
Right. Right. So this is I can get you a list of important decision that you probably uh, you or someone else, right, decided. Okay. When you are born and you are die, probably you don't decide, right? So but the others, you are involved in those decisions, right? And these are probably not exhaustive list of something that is important, okay, to decide. For example, select school, okay, or university. It will shape you. Select the field of study, okay, when you enter IPE, for example. Uh, One day you will select a house, or you probably don't select. You will stay there forever. That is the same thing, okay? That default, right? Not selecting is the same as selecting, okay? And then where you want to settle down, for example, you probably want to go abroad or somewhere, and then select the spouse to be, okay? Selecting the thesis topic, because that is will be in your curriculum vitae forever, right? They will always ask you what is your thesis topic, and then career, the job, and then selecting your friend probably, yeah, or you select to change the career, or selecting certain investment, okay, or to select to have a child or not. These are example, or another example, when are you going to marry or not? Yeah? So these are the example important decision in your life that probably you want to use decision analysis. Okay? Why? Because this is important. So as take out, okay, this is our last slide for today. Decision is a conscious, irrevocable allocation of resources with the purpose of achieving a desired objective. So this is very important, this definition. Decision is conscious, meaning you make decision based on your consciousness. Okay? You don't just ignore. And then second important characteristic of decision is irrevocable. That means once you decide, you cannot take it back. Okay? So decision is similar to your deep thought. Okay? Before you put your bet on the gambling table. Okay? Once you put your bet, meaning you already decided, okay? So just waiting for the outcomes, the consequences, that is no longer decision. Okay? So a decision maker, of course, a person or a team, not necessarily one person, that with responsibility and authority to allocate the resources and implement that decision. Okay? This is important definition. Why? Because sometimes, especially in Indonesia, okay, I just noticed just when I come back here, okay, people get why decision in Indonesia have a lot of problem is because they don't understand the meaning of decision. Okay, remember, you only have responsibility without authority, then you are not a decision maker. You got it? You cannot just have responsibility without authority. Okay. The same thing, okay? People make decision, they will think that, oh, I will make decision, I will try first. Joy a while ago said like that. Okay? I will try first, and if I fail, I will come back again. That is not a decision. That is because decision supposed to be irrevocable. Okay? You cannot take it back. Okay? Once you decide, it's there. You already allocate the resources, it's there. Okay? The resources can include the money, can include the time. Okay? So like Putin decided to attack Ukraine, so that's a decision. Right? Okay, so that's all for today. So next meeting we'll continue this topic. Okay? Thank you for your kind attention.
Okay, thank you, sir.
Yes.
Don't forget you will present next week.
Oh, yeah.
Okay.
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 Thank you.
Bye.